So in this video, I'll be showing you how to calculate normals on the displaced plane mesh using a spatial shader. For those who don't know what a normal is, real quick, a plane or polygon is made up of two dimensions. The normal is the other one. In computer graphics, normals are used to determine how light interacts with them. The closer a normal is to pointing at a light source, the more that light source will illuminate that polygon. Something that confused me at first was that there was one normal per vertex, instead of per triangle. Later on I realized that this was necessary to make mesh look smoother than they actually are, by having the normals on vertices that are shared between multiple triangles averaged out between the directions each triangle is facing. We don't have to get into that in this video. Just remember, if you want an object to have flat shading, each triangle needs to have its own unique set of vertices. When shading some objects to look smooth, calculating normals can get fairly complicated. Fortunately, this isn't the case with terrain, at least not with the terrain that we are creating. Since it starts out as a single plane with vertices that are only moved up or down along the y-axis, we can calculate the normals on each vertex by using the difference between it and its adjacent vertices. In this shader, we don't have easy access to the vertices other than the one the vertex function is working on. We do, however, have access to the height map used to determine their heights. So we'll add an amount to the x and z of the vertex built-in variable equal to the distance between it and its adjacent vertices, and use the result to sample the height map. This distance will increase as the mesh's detail decreases. I'll start by creating a new function called getNormal. This will take the vertex that we are calculating the normal for, and the distance between it and the adjacent vertices. Then I'll get the position of the vertex up the x-axis by adding a vec3 with the distance as the x value. I'll call this west vertex, then I'll get the height of that vertex and set the result to its y value. Now I'll do the same but along the z-axis. Then we get the cross product of the adjacent vertices minus the center vertex and normalize the result. You can add the cross product of other adjacent vertices in the normalize function for a more accurate calculation, but 2 seems to work just fine. It's important to note that the order in the cross product function matters. Imagine we're staring at the center vertex, then moving to the north, then the west. This would be counterclockwise if you're facing the front of the terrain. Make sure you follow this pattern or you'll get inverted normals. Also make sure to calculate the height of the vertex before passing it into the normal function. Now you notice that as the mesh gets further from you, the flatter it looks, and it doesn't look very good. This is obviously because with fewer normals, there is less variation and detail in the shading. The solution to this is to calculate the normals in the fragment function on a per pixel instead of per vertex basis. So we'll create a variant vec3 called vert, then assign it the vertex's value in the vertex function. This variant will interpolate across the area in between the vertices. First we'll need to calculate the height at that interpolated point in the fragment function and set it to the vert's y value. Then we'll calculate the normal. The distance will be constant, just setting it to 1 works fine. Now there's no way of setting normals in the fragment function, but we can set the pixels of the Normalmap. We can use this function to convert the normal to a normal pixel. Now this method is much more graphically expensive than calculating per vertex, but I think the results are worth it.